compressed ratio will be given by this B bar B dash, where B is the number of bits which is being compressed and B dash is the number of bits compressed, right? These are uncompressed, these are compressed, and division is the compression ratio. Now redundancy, we take advantage of redundancy in the input image, and they may be the type of coding redundancy, spatial or temporal redundancy, or irrelevant information. For example, in this case, this has a coding redundancy. So from 0 to 255, only a few gray values are present, like with this 1, 2, 3, or rather this only 3 type of. We can represent using short code words with few bits only. In this, we have spatial redundancy. All gray values are present, but pixels along each row are the same. That is, if you know the value of the first pixel, you know the whole row. And then this is the irrelevant information. How irrelevant? Only a few gray values are present, clustered among only 128, and could represent using a constant 128, and would look the same, right? So as we just talked about this coding redundancy, we use short code words instead of long ones. So we can use variable length codes so that most common values have shortest codes, and this average bit width is given by this average bit length actually is given by this expression, this L R sub k, and the probability of this R sub k. So let us take an example that if this is R of 87, 87 is the binary value or digital value. 128, 186, or 55. I showed you there are 4 types of different grayscale available. So 87, 128, 186, 255. The probability of having it, you can easily find out through this or histogram. So these are the probabilities, and these are the code which we actually use to represent them. And these are the number of bits, right? 8 bits we require. But now we are trying to reduce this. So let us have some other code. This 87, we can use only 2 bit. For 128, we can have 2 bit. 186, 3, 001 for 255. So the length of this is 2, 1, and length of this is 3, 3, and 0. So we don't require any of these other than this 87, 128. 186, 255 we don't require. That is why we have placed it 0, and we don't require any code. So what will be the L average? This will be equal to the number of bits used, that is 2. This 2 into what? Probability, 2 into 0.25 like this, and 1 into 0.47 like this, and just add them, we'll get 1.81 bits. So what was C? As I just mentioned, that C was the compression ratio. What was that? B was equal to number of bits uncompressed by this number of bits compressed. So these are uncompressed, means 8 bits we were using, and 1.81 is compressed. So we get a huge C, that is 4.4. Then measuring image information, we can compute the theoretical minimum number of bits which is needed to code an image also. This is theoretical computation. First we consider an event E, and if event is unlikely to happen, then the probability is very small, that is 1 by P is large. So when the event does occur, it is significant and provide us with a lot of information. So we define the self information of event E by giving, this is the information, by giving log 1 by PE, and taking minus, this will come up, minus log PE. This is how much information is attached to a particular event E, this event E. For example, if PE is half, what we say? We have this I equal to 0 bits, so we require 0 bits. For PE it will be 1 bits, for P equal to 1 by 4 it will be 2 bits. This is log 2, so 2 square is 4, that is why. This is how we can get the theoretical minimum. And so say we have a set of random events drawn from a possible set of values A1 to AJ. So we will call these the source symbol. So they could be randomly generated from a transmitter, and the probability of each of these can be PA1, of generating these symbols PA2 and PAJ. So the information carried out by single segment, as I just mentioned, this will be minus log PAJ, which is probability. So assume that events are independent. The average information per symbol is given by minus P log P. And what is this? This is a kind of entropy only. So this is entropy. For images, the event R0 to RL-1 are possible if they are possible gray level values. We can use the histogram to estimate the probabilities of the symbols. So the average information per pixel, this is also called the entropy of the image, just mentioned. This is nothing but PR means P sub R or sub K for each K log base 2 and this PR RK, right? So this is the probability and this is the PR RK. I'll show you with an example that what will be the value of H, that is the entropy or the average information per pixel. For example, if you have 8 gray levels, same probability for all values, that is P0 to P7 1 by 8. What will be H? We'll place P this probability, this bit. 8 gray levels are there, and probability for each of this is 1 by 8. Say 1 by 8, and this will be log 1 by 8. That will be equal to minus 3. So place minus 3 here. So it will be 3 bits, right? And for this particular example, 8 gray levels, but only one has non-zero probability, say level 1. So P0 to P7 they are 0. So P0 to P7, because there are 7 numbers, 7 into log 0 for every this is 0, and 1 will have a probability of 1. So we'll take 1 and log base 2 of 1. This is again log 1 is 0. So this will be 0 bits. This is how we are going to find it out. Let us take one more example, because that might be confusing for you. So we have already seen this example, right? This is the probabilities. These are the code we have used. This is the number of bits initially, but now we say that we are using these codes, and this will be the number of bits. So we will use this formula. How we are going to use it? Just we use this RK, means the brightness values, and this will be like this. We just place all values here. In the probability from this column we take here, and we find the log of this PI. So we find out log of each and every term, right? And then we multiply it with this P, right? After taking log P, we multiply it by P. So say 2 into 0.25 will be 0.5. And because this is minus, we continue doing this multiplication, and finally we add them. So it will be 1.66 bits. Okay, this was H bits, which is let's see, a huge what we say, improvement. So this is the fidelity criteria, because root mean square error we need to find, because an objective measure of error between original and compressed image has to be seen. This is the root mean square, this is the half hat, this is F, and the difference of these two. So we also have known that this is the signal to noise ratio. This was F hat, and this is the root mean. So and subjective measures like rate quality on a scale from 1 to 10. So these are all the fidelity criteria that may be employed. So image compression and decompression model, because we are talking about compression. So this is our image. Okay, you can take as fx, y, and also time also you can take. Now this is the mapper. What you do, you transform data to a form that can be more easily compressed. For example, Fourier or Lagrange transform. Then you quantize it. This reduces the amount of data and throws away smallest transform coefficients. And then we come to the symbol coder. This codes the resulting data using the shortest code words, that is variable length coding. So this is the compressed data for storage and transmission. This is how it is done, and after that you can decode it, so you can get the initial image. So this is the image compression and decompression model. So now we have this various lossless compression methods. Lossless means the compressed image can be reconstructed exactly. So we'll look at these methods one by one. Huffman coding, arithmetic coding, LZW coding, and run length coding. So Huffman coding, it takes advantage of coding redundancy. So generates a variable length code as close as possible to the theoretical minimum length, and doesn't take advantage of interpixel redundancy. Very important. Huffman coding does not take advantage of interpixel redundancy and widely used as a component, that is the symbol coder in many compression methods. The algorithm is, how do we do it? We find the gray level probabilities, we order the probabilities from smallest to largest, we combine the smallest two by addition. We repeat again these two and third steps until only two probabilities are left, and by backward or working backward along the tree, we generate the code by alternating assignments of 0 to 1. Let us take an example. What we do is, these are the probabilities, these are the symbols, and we start with gray level probabilities. We sort the probabilities from largest to smallest. These are the probabilities. What we do, we sort them. So 0.4 is the highest, 0.04 is the lowest. So what we do, we combine the last two one. This is 0.1, again it comes here. We combine these two, it comes to 0.2. We combine, now this 0.2 will take the position because we are ordering it every time. This 0.2 will come here. So we do it, we combine again and again, so that we get only last two one probabilities like this. Okay, this simple 0.2, 0.1 will be added to 0.3, and this 0.3, 0.3 will be added to 0.6, and it will take the position above because this 0.6 is higher than 0.4. Right? You understood? Now, how we are going to backtrack it? We backtrack it like this. We assign 0 to 0.6 and 1 to 0.4. This 0.6 has come from 0, 0. Right? And this 0, 0, if you backtrack it, it has come from this, again, this 0.4 has come from, 0.4 is come from this 1, and we backtrack it and we go to A2. So for 1, we have code as A2. And for 0.6, we come to 0, 0, we backtrack it and we come to A6. So A6 has 0, 0. Again, now when we try to find out this 0, 1, we go to this point. It has come from 0, 0, 0, 1, 0 and 0, 1, 1. We backtrack it 0, 1, 1. We backtrack it 0, 1, 1, and we see it has come from A1. So now A2 will be assigned code as 1, A6 0, 0, A1 0, 1, 1, and like this. All these codes will be assigned. Okay. So once these codes are assigned to each A2, this A2 to A5, all these codes are assigned. So we can generate code sequence for symbols A2, A1, A3, A1. For example, this A2 will be what? A2 will be 1. So it will be simply A1, and this A1 will be only say 0, 1, 1, 0, 1, 1, and A3 will be 0, 1, 0, 0, 1, 0, 1, 0, and A1 again will be what? 0, 1, 1. Sorry for the for these numbers. So this is how we can make A2. These are the numbers we can easily generate, and we can decode the signal sequence also. If this is the sequence 0, 1, 0, 1, 0, this will be our A3. This will be A3, and let me draw it. This will be A3. Then this 0, 1, 1 will be A1. Then this 1, 1 will be, or rather, these values will be 1 and 1. This will be A2 again, A2. Last one will be A6. So this is how we can generate and decode. Now what will be the average length of the code? This is 1, and the probability is 0.4, 1 into 0.4. This is 2, 2 into 0.3, 3 into 0.1, and like this. So this is around 2.2 bits per symbol. Now we can compare to the theoretical minimum. which we know we computed by the entropy. So what we'll do, we'll take the log of this pi, this will the value, and minus p log pi, we add them. This is 2.14. So this is, you have known, this is a huge, we have achieved a very good 2.2 rather than 2.14. This is always a good value. Now we can find out the Huffman code. How to find out the Huffman? We have these gray levels and these are the probabilities. So what we do, we find the gray level probabilities, sort the probabilities, combine the smallest two by addition, repeat step 2, 3 until only 2 are left, work backward and generate code. This we have shown you. This is again an example. You know how to make it, you can backtrack it, you can find out the value. These are the codes which will be used only. This also you can find the L average by just multiplying this value with the number of values you have used. So this is this should be greater than or equal to the ideal one. H is equal to minus p log pi sigma. Now arithmetic coding. This is the sequence of values is assigned a single arithmetic code word, and the code word is a fractional number between 0 to 1. How this is being known, I'll tell you. Each symbol is assigned an interval based on its probability of occurrence, and code words are of fixed length. So let us see how it is done. So what we do, if this is A1, we make a scale like from 0 to 1, right? This is from 0, this interval is from 0 to what? 1. So we make from 0 to 1 and we assign this A1, A2, A3, A4 according to the interval. Now this A1, right? This A1 has value from this subinterval of 0 to 0.2. So this particular A2, we have to do what? We have to see that this A2 is from 0.04 to 0.08. A2 is from 0.04 to 0.08. So we again divide it. Now this A2 is 0.04 to 0.08 because this is coming after A1. We are using this message, right? So this is okay, A1. Now if we want to go to A2, we have to divide this into these number of values. Now A2 will be having this interval. Now coming to A3. A3 is what? A3 is 0.4 to 0.8. This is 0.4 to 0.8. So we have to again divide this A3 with these values. Means to scale with these values. Then again A3 is coming. We have to again divide it. And coming to A4, this is 0.06. So 0.0688 to 0.06752. So this is the A4 value, last one. So with each new interval, you find the subintervals by multiplying the total interval by the probability of each symbol, and then add it to the lower bound of the interval to get the upper bound, right? Like this. This is how. This is A1, this is A2, computed with this value, then A3 computed by this value, A3 again computed again, then A4 computed again, and this is the mid value. So we can use this 0.068 as the value of our choice, right? Now once we get this value, the final code word is this value. So we have 3 decimal digits for 5 symbols. How many symbols are there? 1, 2, 3, 4, 5, and we just have 3 digits. You see, only 3 digits for 5 symbols. So 3 by 5, that is 0.6 symbols or digits per symbol. So equivalently we have 1.99 bits. Okay, that is 10 to the power 0.6. We will use this 0.6, and 10 to the power 0.6 is equal to 2 to the power 6. That is x equal to 1.99. This is how we get this value. This is x equal to 1.99. And if you want to find out the theoretical value, this is take these values p log p minus p log p and add them. This is a theoretical value, 1.92 or 0.58 digits. So hope you understood this. If we have this A1 that we need to, that can be encoded as what number, just go ahead, take this as for A1 0.2, again with these values divide it again with A1, divide it again with A1, and take the center value, that is 0.04. This is the sequence. Now coming to this LZW coding, this stands for Lempel-Zipf-Welk. So this works by coding short string of data and this is used in GIF, TIFF and PDF file formats. So it creates a dictionary of code words. For 8-bit image, for say, the first 256 words are assigned to the gray values 0 to 255. As sequence are discovered, new code words, that is maybe 256 through 511, are assigned to represent them. For example, the sequence 126 may be assigned to a code word 256. I'll show you with an example. Say, what we have done, this is the original image. Now these are the value of dictionary. These are the entry values. So till here, this is known to you. We enter this 0 to 255, 0 to 255 value here. But what about while we go from first position, we traverse from first position. We see that 39 and 39, this is coming. This is a sequence. Again, if I move around, 39 is coming 1, 2, 3, 4 times. So we assign an entry to this dictionary index to this entry 39 like this. Okay, 39. For 39 to 39, we assign the value 256. So directory entry will be 39 and 256. Again we traverse, we see that we find this 39, and after 39 it is coming 126. 39 after 126, 39 after this 126. So this is again a pattern. So what we do, we take this or enter this value in the dictionary entry, and now 256 is already been taken. 257 this will be the dictionary location or the index, right? In this way, these sequences will be provided these numbers like this. Okay, 39 to 39, this will be 256, and 39 to 126, 257. So all these sequences will have some of the other number. And now this is the original image, and if we want to code it in LZW, it will be coded like this. So 39 to this 39 to 39, this will be not 39 to 39 but only 256. And if we find this value, this 259, we say that it is 126 to 39. So again we get this 126 to 39, or it is 126 to 39. So we only write this 256 value, right? This is LZW. So this is you might have seen, this is very good as far as decompression is concerned. This is lossless. Finally, coming to this run length coding, this uses interpixel redundancy, that is usually used for binary images, but this can be employed to grayscale also. Or we output the number of consecutive zeros along a row for the number of ones. For example, in this case, what we have, these are a number of zeros. How many? 8. How many number of 1? There are 0 zeros. There is no 0, so we write 0. Number of 4s are 4s. Number of zeros are 4. Okay. Here we have number of zeros as 1, and number of these ones are 2. Number of zeros are 5. So this will be the output code. So this is best case for compression. If the rows are all zeros, but it is worse than the original image. If we have all these, we have sequence like 0, 1, 0, 1, etc. Right? So this RLC is applied for to non-binary images. If we want to apply it, this is the m-bit image. The gray values are like this, from A0 to AM-1 to the power 0. So we apply RLC separately to each bit pair. So this can be a problem in areas where values fluctuate about certain transition points. For example, this 127 can be written by this, but as we go directly from 127 to 128, the whole plane change. So each bit keeps flipping from 0 to 1. This is an example. See, this is bit 7, this is bit 6, this is bit 5. So this is the variation if we take grayscale coding. So we use gray code. We first code the image using the gray code rather than the normal binary code. What are the gray code? Each adjacent code words differ only by 1 bit. So if a pixel differs from its neighbor by 1 gray level, only 1 bit in the gray code is different. So how to do it? Let us see. This is 2-bit binary. This is 2-bit gray. See, only when we move from one point to another, only 1 bit is changing. So how we get it? We replace this from here, from to here. This is the 2-bit gray. And how we find the 3-bit gray code? We just place these values and from here to here, invert these values, right from 10 to 110101, and once that is done, we place 000 here, 111 here. This is the gray code. So the result will become somewhat finer in this case. So hope you got the idea of this lossless compression. Thank you so much. Take care.